Hello there and welcome back to this video series on control systems. We have seen that Bode plots include two plots actually drawn to a common omega axis, omega versus m decibels plot and omega versus phase angle plot. Okay. In these two plots, omega is plotted along log axis on semi-log graph sheet. This is in decibels and phi is in degrees. Okay, we need to remember that same omega is plotted on log axis and is common to both MDB and phi plot. We saw that it's very easy to read crossover frequencies and gain phase margins and very easily infer about stability by noting that these must be greater than 0 for stability. It would be best if you watch videos 54 and 55 once again, take notes and keep the notes handy before watching this video to make the best out of this video. This video essentially discusses drawing asymptotic Bode magnitude plot. We will come back to the phase plot at a later time for a transfer function consisting of first order terms alone. So Bode magnitude plot for first order terms, that is what we are going to see in this video. We will see 3 example problems, and through those example problems we will bring in several features of this asymptotic approximation. Essentially drawing Bode plot involves lot of computation, but fortunately there is a easy method of drawing the Bode magnitude plot using what we call asymptotic approximation. We will try to see what is this asymptotic approximation with the help of 3 examples. Let us see the first example here. It involves a first order term in the denominator. Remember this point 1. This point 1 is the time constant of the first order term in the denominator. We call this tau. Okay. Later when we refer to this, we will say tau, the time constant in the denominator. We write the sinusoidal transfer function, and then we try to explain the approximation scheme by showing both the approximate plot and the exact one on the same graph sheet as shown here. The red one is the exact graph, that is you compute maybe 100 or so magnitude values at different frequencies and join them by a smooth curve, that is the exact one. This blue dotted one is approximate graph. We see that there is one 0 dB per decade line, and you see there is another line. This line is going down. This line has a slope of 20 decibels per decade. Okay. This duration separated by two frequencies omega 1 and omega 2 is called 1 decade when omega 2 by omega 1 is 10. So from here to here is 1 decade because 10 power 0 by 10 power minus 1 is 10. Similarly from here to here it is a decade because 10 power 1 by 10 power 0 is 10. So from here to here is 1 decade, from here to here is another decade, from here to here is another decade, from here to here is another decade. See, at the beginning of the decade the value of the magnitude is 0. At the end of the decade, the magnitude fell down to minus 20 decibels. So we say in 1 decade it reduced by minus 20 decibels. That is the slope of this line. So this entire exact curve can be approximated by 2 line segments. One at 0 decibels per decade and another at minus 20 decibels per decade. Their meeting point is called this corner frequency. You can say that this corner frequency is 1 over 0.1, 1 over tau. So if you have a term of the form 1 plus tau s, you will have a corner frequency 1 over tau. 1 over 0.1 is 10. And the maximum error occurs at this corner frequency, and this error is very little, 3 decibels. 3 decibels over 40 is very small, less than maybe 10%, 8% error. Okay. So we say that if we have a term 1 plus tau s in the denominator, the approximate line has a slope of minus 20 decibels per decade. This is the blue line with minus 20 decibels per decade after a corner frequency of 1 over tau. Tau in this example is 0.1. So after 10 it is minus 20 decibels per decade. Okay. Similarly, if you have a term 1 plus tau s in the numerator, the line will go up at a slope of 20 decibels per decade after the corner frequency 1 over tau. In the next example, you have two first order terms, 1 plus tau 1 s, 1 plus tau 2 j omega, 1 plus tau 1 j omega, 1 plus tau 2 j omega. Corresponding to this term, you have 1 over tau 1, 10 radians per second is the corner frequency. Corresponding to this term, 1 over tau 2, that is 1 over 0.01, that is 100 cycles per second is the corner frequency. We will show the exact plot, approximate plot, and then we will present our inferences. That way I think it will be easier. Let us go to that plot. This blue line is the approximate plot. This blue line has 0 decibels per decade. You can see at the beginning of the decade it is 0, ending of the decade is also 0. So this line is 0 decibels per decade line, horizontal line. Similarly, here the magnitude is 20. Here also it is 20. So 20 minus 20, 0 decibels per decade. You can see that this corner frequency is 10, that is 1 over 0.1. This corner frequency is 1 over 0.01. Okay. Now you can see that at this corner frequency on the left you have a 0 decibels per decade, on the right you have 20 decibels per decade. So a net increase of 20 decibels per decade is present here. So this corner frequency goes into the numerator. Here to the left of the corner frequency it is plus 20 decibels per decade, to the right of the corner frequency 0 decibels per decade. So the slope decreased. Because the slope decreased at this corner frequency, we can say that this 10 square 100, that is 1 plus 1 over 100 s is in the denominator. We can also see a few details. The maximum error occurs here at 3 decibels, and again from here to here is 1 decade, up till here is another decade, from here to here is 1 decade, from here to here is 1 decade. You have this 10 power 1 is 1 corner frequency, and the place where another maximum error occurs of 3 decibels, this is another corner frequency. This is just an explanation that we have seen all through with the help of the plot. I would suggest that you go through this very carefully, make notes, understand, and commit them to memory. We will see a third example. The third example included several other terms. It included term 1, constant term. This is term 2, first order term. Term 3, which is a lone s term, and term 4. Let us begin writing the magnitude of this sinusoidal transfer function f of j omega. It will split nicely into 4 terms because product of the terms becomes logarithm. In the logarithm, sum of the logarithms, and coefficient of the terms becomes subtraction from one another. That is why these two have plus sign and these two have negative sign, because they correspond to the terms in the denominator. So what we'll do is we'll build a table for different values of frequencies and list what is the contribution of term 1, term 2, term 3, term 4 and sum them up in the total here. It may look complicated, but I would encourage you to draw this table once or twice on your own without looking at all this, and then you'll be good to go. So what I would suggest is take down this table and leave the blanks here, and you can fill them up when I ask you to do so. Okay. This term 1 is constant. It is 20 for all the frequencies. This doesn't involve omega. This is a first order term with a corner frequency of 1 over 0.5 is equal to 2. So up to 2 it is zeros. From 2 onwards it will increase by 20 dB per decade. One decade from 2 will be 20, 200. So from 0 to 20, 20 to 40, that will be 20 decibels per decade. We need to fill what are these values. At omega is equal to 10, what is the value? At omega is equal to 100 and 1000. Let us say this value is x. Okay. You can say the slope of this line is plus 20 decibels per decade because it's in the it's adding. You have a plus here. So x y2 minus y1, that is x minus 0 divided by x2 minus x1, 10 minus 2. But remember, these are logarithms. So though we write it as 10, when we show it on graph sheet, it is logarithm of 10 minus logarithm of 2. So y2 minus y1 by x2 minus x1 is equal to 20 for this term. So x is equal to 14. Put that x there. Now you write it on the table. Similarly, you have a term y here. y2 minus y1, that is y minus 20 divided by x2 minus x1, log 100 minus log 20 is equal to slope of this term 2, that is 20. Y is equal to 34. Now you write the value of 34 in the place there. Now assume there is z there, and z minus 40 by log 1000 minus log 200 is equal to 20. So z is equal to 54. And similarly, you write down equations for this. Term 3, you can do it very easily. 20 log omega. So corresponding to 2, you can write 20 log 2, 20 log 20, 20 log 200 or so. Or you can see its slope is minus 20 decibels per decade. You can use that. You can use that to find the value of the missing place, missing quantity here. So let us say it is P. So P minus 0 by log 2 minus log 1 is minus 20 because this term is in the denominator and you have a negative sign. So you compute P is equal to minus 6. Put that minus 6 in your table. Then this term is, let us say, is Q. Q minus of minus 20 is plus 20 minus log 20 divided by log 20 minus log 10 is minus 20. So Q is minus 26. Put that minus 26 there. Similarly, let us say this quantity is R. R minus 40. This is R plus 40. Log 200 minus log 100 is minus 20. So you can write down minus 46 there. So this last term again contributes one corner frequency, 1 over 0.01, that is 100. Up to 100 it is a 0 decibels line. After 100, for the next decade it will go to minus 20 because it is minus 20 decibels per decade. 0 minus 20 is minus 20. This quantity we need to fill. We will fill it here and you can write it down. I will just show you in a second. T minus 0 divided by log 200 minus 100 is minus 20. So T is minus 6. You can put it there. Now the table is complete. corresponding to each value of omega, the total you sum up 20 plus 0 plus 40 plus 0. Okay, we will write that down here systematically. So sum all these, you get 60, sum all these, you get 20, sum all these, you get 14, and then 14, and this also 14, this also 14, this is 8, and this is minus 6. Now you draw the magnitude plot to show this along the log axis, this along the other linear axis. The plot comes out like this. A beauty of this method is that once you have this plot from experimental data, looking at this plot you can back compute the transfer function. We will see that as a topic later, but for now we will show the exact plot superimposed on. You can see they are almost coinciding except for two errors, 3 dB and 3 dB here. With that, we can summarize and say that it is possible to approximate Bode magnitude plot to reduce the amount of computation by using asymptotes. Such plot is called Bode asymptote magnitude plot. May be approximated as BAMP. The maximum error of approximation is 3 decibels. And if you have experimental data to show the magnitude plot, the transfer function may be inferred by back computing. I think that's all we have for now. Have a great day.